there have been a slew of decarbonization reports over the past couple of years, looking at different pathways to reach net zero emissions in the United States by 2050. So our study is a bit unique because of its high degree of geographic and temporal granularity, and with the hope of really making these transitions understandable on a human scale of what it takes for the US to achieve net zero. So what do these transitions imply for how Americans use energy and how that energy is supplied? And we also wanted to quantify and explore the inherent challenges and opportunities. And so the granularity of our modeling allows us to assess at a state and local level implications for things like infrastructure build out. So where do we site new transmission and wind over time? What happens to thermal facilities over time? We also look at effects related to land use in addition to employment and workforce development needs, as well as air pollution related health impacts. So we modeled alternative techno-economic pathways to achieve net zero emissions in the United States by mid-century. So we used what's called a macro energy systems model to create these pathways. And so these types of models are becoming increasingly used in policy agenda setting and planning. So at a high level, these models select least cost technological pathways to achieve emission targets over time. In other words, we're optimizing for total system cost over the life of the transition to select technologies over time to meet future energy demands. So this slide shows primary energy supply currently and in 2050 for different futures. So all of these pathways or scenarios employ 6 key pillars of decarbonization. The first is increasing end-use energy efficiency and electrification, although to varying degrees. The second key pillar is deployment of wind and solar generation in addition to transmission and firm power, so building out a clean electricity system. The third key pillar is build out of the bioenergy sector and supplying other zero carbon fuels and as in addition to feedstocks. And the fourth key pillar is building out our CO2 infrastructure system. In addition, we look at another key element of these pathways is reduction in non-CO2 emissions like methane across the natural gas supply chain, in addition to enhancing land sinks. So in this figure, we show the overall annualized energy system costs as a percentage of the total gross domestic product. So you can see historically what happened from 1970 to 2020 in black, and then you can see our future scenarios. So based on our assumptions, all of these scenarios show annualized system costs as a share of GDP that are in line with our current levels. So this figure also suggests that some scenarios may cost a little more due to certain technologies being excluded or constrained. And so the modeling that we're doing benefits from both perfect foresight and the capacity to seamlessly integrate energy supplies and demands across sectors. So while we find that annual energy expenditures remain affordable, the net zero transition requires substantial upfront capital investment. So nearly $3 trillion in capital will need to be mobilized for energy supply infrastructure in the 2020s alone, or more than double a no new policies reference case scenario. By 2050, the cumulative supply side capital investments reach as much as $14 trillion, or almost 4 times the reference scenario. So deploying capital represents a potential challenge. So project proposals must be de-risked through a sequence of investments to conceive, site, and design projects, prepare contracts, and obtain permits prior to final investment decisions. And in the net zero scenarios, America's scenarios, we estimate that about $190 billion in pre-FID capital is needed in the 2020s alone, at least double the reference case scenario. So we find that each of these net zero pathways presents challenges of unprecedented change in one or more features of the energy system. So these graphs represent the relative impacts in the 2040s, which helps visualize what our modeling suggests are the largest challenges and trade-offs across pathways. So for example, in the 100% renewables or RE plus case, which is represented in blue, entails the most significant land use for wind and solar, and transmission, and the most extensive addition in addition to our transmission, but also provides the highest level of health benefits and entails greater number of energy-related jobs. All of the findings that I presented and well beyond what I presented can be found at the NetZero America website, which includes an interim report that we released in December, in addition to detailed dependencies on these modeling efforts. There's also a data portal available for downloading some of the data generated through these modeling efforts. And I should also note that a final report will be coming out in July.
Marilyn Brown, who is actually going to be our next speaker, observes this was a great presentation and analysis. She wonders, how do you treat the opportunity to improve the energy efficiency of our buildings, transportation, and industries? Have you attempted to quantify energy efficiency jobs associated with the transition? As you know, energy efficiency is labor intensive and the jobs would be spatially ubiquitous.
Mm-hmm. And so what I presented is only supply side jobs, so it doesn't include transportation related jobs like related to manufacturing and sales and those sorts of things, and it doesn't include energy efficiency improvements. We are doing a follow-up study right now where we're building out the modules for transportation related or automobile manufacturing and energy efficiency related improvements. Energy efficiency related improvements are a bit difficult to model the employment effects, like many studies do, but they're very difficult to model in any sort of well substantiated way. So we're working through figuring out how to do that in a supported way. Yeah, but they are substantial. Yeah.